For coming, and I'd like to thank Professor Ohm for inviting me to KAIST today to give a seminar. So today I will talk about a problem. My co-authors are Sunil Fujita and Amita Saka, about finding large, highly connected subgraphs when we know some sort of condition about the sparseness of the host graph. Okay, so here's the question. So if I have a graph of order n and independence number alpha, then how large a k-connected subgraph can I find in G? So how large in terms of order, and k, this is a vertex connectivity. So if I know the independence number, so that kind of somehow measures how sparse the graph is. So it's a very natural looking question to ask. So let's take a first observation. So if we just consider taking alpha cliques, each with they're all about the same size, so either ceiling or floor n over alpha. And then if n is at most n over alpha k, then we cannot get is it chalk? Then we cannot get a k-connected subgraph at all. So just this first simple example. So if n is at most n alpha k, then there's no k-connected subgraph in this example. And if we have more than alpha k, then the best that we can hope for is, well, the biggest is n, ceiling n over alpha. So in general, we cannot hope to get more than ceiling of n over alpha for the answer. And the problem is only interesting then if n is greater than alpha k. And then some more observations. So k is 1 is trivial because you can just take the largest connected component in the graph. There's only at most alpha components. And also k is 2 is not too difficult. We can prove that by considering the block decomposition of the graph. We can remove an n block and apply induction on alpha. So it's true if n is greater than 2 alpha, and this cannot be weakened to say 2 alpha because we can take the path with 2 alpha vertices. So that's got independence number alpha, and there's no 2 connected subgraph. So if I have to, I can assume k is at least 3. All right, so here's a first result. So it says the following. So if k and alpha are at least 2, and G has more than alpha square k vertices and independence number alpha, then n over alpha ceiling is indeed the correct answer for the largest k-connected subgraph. So let me give a rough sketch of this proof. So we kind of go by contradiction throughout. So suppose G itself is not k-connected. So then we have a cut C for G like this, and A1, A2, each one non-empty. We don't have any edges between them. And this is a most k minus 1. And it's not too hard to show that the 2 independence numbers have to sum to alpha. So if alpha 1 and alpha 2 are the independence numbers, then they have to sum to alpha. And also the sizes of the two subgraphs would be approximately the proportion alpha I over alpha times n. Yes, so about this big. Right. So then one of these will be too big. Having this condition, one of these two parts will be large enough, so it cannot be k-connected. So let's say alpha 1 is at least 2. Yes, then it's too big, so it cannot be k-connected. So we can continue to split up these sets here. So I can say split up A1. So here's another cut for A1. And I can move this cut over to C. So this is at most k minus 1. Move the cut over to C. So then I get a new thing here now is at most 2 k minus 1. I got 3. And then you can guess what happens. A1, A2, A3. The 3 sum to alpha, and each one's is the same proportion. So just after a relabeling. So we'll get that as the next step. And then we can keep going. So there's no edges. So we can keep going until we get to alpha of these, assuming along the way we do not find the required k-connected subgraph. So I can continue this process, and I end up with, I just continue here, with alpha of these sets. So alpha. Okay, so the sum of them will come to alpha. And here I will have alpha minus 1. So I'm going to call this C prime. And now the sum of the independence numbers is alpha, so each one must be a clique. So each independence number is 1. So we have this situation now. So we're at this stage here. There's no edges between any pair. So this we can show somewhere along the way. This is needed, like for an induction argument, and this is also used to say prove this here. So each clique has more than k vertices, and now notice that for any vertex in C prime, the vertex has to dominate one of the cliques. Otherwise, we have alpha plus 1 independent vertices. Right, so let's say it dominates A1, and then it follows that, in fact, we can find a partition of C prime, say D1 up to D alpha, as I have right there, where DI, every vertex of DI dominates AI. So to that one, actually. That one. Okay. And now the largest of the AI union DI will be k-connected and is big enough, at least n over alpha. So, please. So that's the proof. So I've missed out a few technical details here, but this is the rough idea of this result. All right. So, okay. So what does that tell us now? Okay. So we've then seen. So if you imagine these are the values of n, So then below alpha k, the problem's trivial. There's nothing to do. The problem's trivial. We don't get the k-connected subgraph. And more than alpha square k, we do get we have solved the problem. We do get the k-connected subgraph on at least n over alpha, and we've seen already that it's the sharp answer. So the problem is also solved on this side. So now the interesting question is, what happens between alpha k and alpha square k? Right, so let's think about if we're a little bit more than alpha k, then can we possibly, in fact, get the n over alpha for the k-connected subgraph? So maybe not surprisingly, the answer is no, we cannot. Because otherwise the problem would be completely solved and I would have finished by now. So yes, the alpha square k maybe is a rather weak lower bound on n. And can we possibly drive the lower bound all the way close to alpha k? So for a start, I'm going to tell you that we cannot go all the way down to alpha k, because I have a construction, as this lemma says. If alpha is 3, I need k more than alpha, then we can have a graph G on about a little bit more than 2 times alpha k, with no k-connected subgraph on the n over alpha. So in fact, let me just divert here and mention that. So I've been actually visiting Professor Borenpark the last 2 weeks, and we've been discussing this problem. And she actually found a better example. I think we checked and we didn't find any mistakes, and so she managed to increase the 2 plus epsilon up to 9/4. And in fact, we don't need the k more than alpha here.
Are these constructions or these are random?
Constructions explicit. So I will be showing you in a moment. I still reckon this might not be optimal, but it obviously beats this one. So I have to maybe double check this, but I think it's correct. So maybe I can mention a little bit about this one in a moment. But let me just mention this one. So here's an example for alpha is 4. So what happens here is we have alpha minus 1 of these lines here. So we have every circle is a clique, and every thick line between 2 circles means every edge is present. And these are all the sizes. And let's look at this. So we optimize n subject to b plus c is k minus 1, because the whole graph has to be not k connected, so we choose b plus c as the cut set, right? So we need this condition here. And also the biggest k connected subgraph is this clique over here. So we need to optimize subject to this thing less than n over alpha. So this here is the sum of all of these. And then do a bit of optimization, and we find out that n comes to this expression for some constant c alpha. So for example, if we have 3 and 4, we end up with 6.6 and 8.8. So a little bit between 6 and 8. So 2 times 3, 2 times 4, respectively. Okay? So just comparing back to the 9/4 here. So for 3, for example, it's better. We get 27 over 4, which is more than 6.6. That's 6.75. So this is better for 3, and well, in general, it's better than this. Okay, so let me now talk about thinking, should I show you the other construction now, or I could maybe do that. So roughly speaking,
So when you're trying to show is the construction that's
Borom's
no K
construction.
connected- Yeah,
yes, so this one.
no K connected subgraph of order n least n over
Yes,
alpha
with this number of further size.
with a large number. of
Yes. So it's like this. It's actually, I think that there could still be some constructions that's more complicated, but this is how this one works. So what she did was, like, if alpha is 3, we have a G3 with roughly 27 over 4 k minus 1 further size, and no this independence number is 3, and no k, so above minus 1 or something, so 1 less than this this value, no k connected subgraph on so in fact I will show you what G3 looks like in a moment. So assume for now we have such a graph G3 satisfying all of these, and then furthermore there is a cut set. Well, say, well, okay, maybe at most. This is a cut set of G3. So what she just simply did was to add and then roughly 5/4 here. And then and how many of these there are there? Alpha minus 3 of these. So that was her construction, in fact. So assuming the G3 exists, this will be G alpha. Right? And the independence number is alpha. You can maybe check that. So these are all cliques. And the biggest, so this would be n. You can work that out fairly easily. And there is no k-connected subgraph on n over alpha, because why is that? Because I think it's right, isn't it? No. I think it's true.
Yeah, so if you have a k-connected subgraph, you can I mean, it's only on one side of these k minus 2 vertices.
Yes.
Or k minus 1 vertices.
Mm-hmm.
So either it's in G3.
Either in here or one of these,
Right.
or something. So I think that can be verified. Okay. So let me now go on and talk about alpha is 2 and alpha is 3, and try and in fact prove the sharp results. So here's alpha is 2. Here's the result. So now I assume k is at least 3. And if n is at least 4 times k minus 1 and alpha is 2, then we have the answer. So we have at least n over 2. And so here's a kind of warm-up sort of proof. So similar to this here, if we have G is not K connected, then we have a cut set, and the two parts must be complete because alpha is 2. Okay, and then we divide into two cases. So if both cliques have at least K, then just observe here, in the cut set we can partition into two parts similar to this here, where one part every vertex dominates A1 in one part, and here every vertex dominates A2. So the bigger one of these two would be K connected, if this is true. Otherwise, if let's say A1 is too small, then A2 with some calculation is big enough, and it's a clique, so A2 works. Right, so that's fairly simple. And this result is sharp because here's an example with n is just 1 less than what we had, 4 times k minus 1. And then you can check that there's no, so there are 4k minus 5 vertices, and n over 2 is 2k minus 2, but the biggest that we can only get is D and E here, which is 2k minus 3. So if we drop n just by 1, the previous result is no longer true. Okay, so that's alpha equals 2 settled. Right, so now the main aim of my talk today is to try and prove the case alpha is 3 to you. Right, so this is going to be my challenge today. So here's our result. So k at least 3, alpha is 3, and if n is at least this 27 over 4k minus 1, then we have the conclusion. So now n over 3. All right, now I'm going to show you this graph. So this is actually my G3. This graph will be my G3 as here. And the cut set.
Which graph? Whole graph? The whole graph?
This is G3. This whole graph is G3. And this cut set here is C, 1, F, and B. So if you sum these three, that's a cut set. Okay? Yes, K minus 1. Some of them. And just maybe ignore the fact that these might not be integers. Like, maybe think of K as 3 mod 4 in this picture. Otherwise, we put some ceilings and floors, and we can sort of argue similarly. So this is the cut set, and then to get this we use this cut set as here. That's how this works then. Right. So then this graph we found has alpha is 3, n is 1 less. And the biggest k connected subgraphs there are 3 of them, either this triangle here, or this one, or this one. And in all 3 cases, all of them are 1 less than this n over 3 here. So you can maybe believe me on this. So we didn't come up this randomly. So it came out from the proof that I will show you in a moment. So as you can see, when we get to alpha is 3, we already have a very surprising construction. Like, so this is telling us that dealing with the independence number sometimes just throws up really strange constructions. So this is what we found. And say, for example, if we go up to alpha is 4, this is why I kind of maybe not expecting this to be optimal, because it's kind of relatively simple. We just add 2 more parts onto an existing graph. So just alpha is 4. We get this here, and there might be some other construction which is better than just adding the two cliques. Okay, so let me try and prove this result. So I'm going to say in our paper, this is a 10-page proof. So, so my plan would be to skip past a few claims that I would just put up, but show you how all the claims fit together into a proof. Okay, so let me do the setup. Okay, so firstly, G itself is not K-connected, so I have this as my G. So I have a cut set, let's call it S, and then into two parts. The independence numbers have to be 2 and 1. So this side, let's say it's 1. So with a click, let me call this A2. Right, so I'm going to...
So you're assuming not both are dependent? Oh, okay.
Right.
2 and 1 or 1 and 1 or...
1 and 1 would be trivial. Yeah, so 2 and 1, obviously. Right, so... And then this is 2. And it's... So if A2 is too big, it would be K-connected. So A2 needs to be smaller than n over 3. So here... So here would be roughly at least 2/3 n. So 2/3 n minus k minus 1. So this would be too big. So we have to have a cut set of this here. So like that. So I'm going to call this A11, A12. Both must be cliques. I'm going to call this thing S star. Okay, so we can get these facts fairly easily.
So did we have a bound on the size of click? Or how do you know that A2 is small? Or?
It's fairly large, actually. So certainly so if A2 is small, let's say that, then so in fact let me say this first. So we can as before, we can partition the S star into two parts, where let's say S1 here star, S2 star, and everything dominates as before. Right, so if this happens, then this whole thing would be at least n minus 2. So this whole part here would be at least this. So the larger one would be at least that, and it should be large enough. Or otherwise, so we can either consider if one of them, if let's say A11 is small, then A2 would be large enough. Otherwise, if they're both at least K, then one of them is at least this big, and that's true. Right, so that's how we can eliminate this here. Right, and then to get that, how do we do that? Yes, so to get that, A2. So because A2 we always have this. So to get that second one, I assume this also. So if A11 is at least K, then the larger one of this one and this one would be what we want using this here. So we get 2/3 minus K minus 1 over 2 or something. That should be big enough, right? Or not? Something. Hold on. What's wrong? Oh. Okay. No. I jumped one step here. Not yet. So to get the second one there, so what I actually do is this. So I will define an S3 where, so I've done that. So S3 is defined so that the induced subgraph is K-connected and S3 is maximum. Okay, so I take a maximum set within S such that when I complete together with A2, I get a K-connected subgraph. And then I can, as before, have a partition of the rest where they must dominate like this. Right, so then now to get that, if we assume otherwise, then, well, because this is K-connected, so if A11 is at least K, then the maximum of, so let's max of these two, so A11 well, this is almost n over 3 because it's K connected. So I got 2/3 over 2. Yes. So that's too big. And one of these is would be K connected. So I certainly must have that. And then this one, what did I do? Just some calculation. Yes. Okay, I can show you that. So n minus a. What did I do? So n minus a2. Right. So this is 2/3. This is 3. And then that would give you what you want using our assumption on n. Okay. Right, I can show you that one. So if we define, I have to define a few things before going on. So, okay, so now what I'm going to do next is I'm going to define a set n, which is a subset of S1 and S1 star, union of them, in such a way that, okay, so get rid of this. Right, n is defined to be, and I'm also going to define h. So n is a subset of S1 union S1 star, such that the subgraph h on A1 to S2 star S2 and N is K connected and N is maximum. Okay, and I'm going to define L and L star to be these two sets here. So S1 minus N and S1 star minus N. Okay. Right, so now A11 union how big is that? That I claim is yes, so right, so it's more than n over 3 because this part's k connected and h is k connected, so so they take up at most 2/3 n. So the rest of them has to be more than 1/3, and therefore I can find a cut set for this here. And I'm going to call this B prime, no, B1, B2, and T prime. And then what can we say? Notice that T prime, so that's what yes, notice that T prime has to contain A11 because A11 contains dominating vertices of this here, right? So then, therefore, I must have so I'm going to call B this thing here. So here, this is B intersect L. Well, okay, so where is B? B has to be just two parts here, okay? Hope you can notice T prime has to contain A11 because A11 contains dominating vertices of this set. So therefore the B1 and B2, so the B has to be outside of A11. So it must be there and there, right? And this not too hard to show. We can, yes, just from this. Yes, that's immediate from this. Just take k minus 1 away. And so B intersects L is this here. So in fact, this is L star. This is B intersect L. And so this thing here is non-empty. It's large. All right, so here's a very important fact to notice. So, right, A1 is actually this thing here. A1 is this whole thing here. So I cannot have two vertices in A1 and a third in A1 union S1, S2 with the three of them independent. So if I do, it's that's very easy to see. So let's say I have that. Then what goes wrong? Right, because A2 is at least K, Z has a non-neighbor over here. And this is, so we assume this is independent. So we've got 4 vertices. So that's not allowed. So 3 here is a very important thing to keep in mind. Right, so this one is also not hard to show. So you kind of assume the contrary, and you get a contradiction to this. So it's not terribly hard to show this one. Okay, I'm not going to prove these 3. I'm sorry, I haven't even defined A and A prime. Okay, so A prime and A and T, okay, so A1 union S1 union S2. This set is also big, so we must be able to have a cut set. So right. So as usual here, for both of them, this is at most K minus 1. And these two have no edges between them, and they're not empty. It's just the usual cut. Right, so then with this definition, this is not terribly hard to show. Okay, so 5, 6, and 7. I am not going to prove them, but I will just assume them. Takes a small bit of work, but not difficult otherwise. So it's saying that so this is a good thing to also keep in mind. So A1, no, sorry, A. By the way, we also assume that this is true by symmetry of A prime and B1, B2. Okay, so this is a cut for this here. Okay, so this thing here is that. And then T is the rest, the things outside the A and A prime. Okay, so, now I'm going to divide into 2 cases. So case 1, so we're going to look at in here, and we ask, is there a vertex of B2 in this set here? So the first case is we assume yes there is, and subcase 1 is that there. Okay, so let's see. If I can complete this part. So A prime is at most K minus 1. Otherwise, if A prime is at least K, then we can find 3 vertices, independent vertices that will contradict that the thing earlier. So we can take what we do. So X Right, so we can take two vertices here, and if A prime is at least k, then I can take a non-neighbor of y. So right, by assumption, and then and then x, y, z will be independent, which contradicts this fact here. Okay. So GA is K connected. Okay, so it takes a bit of work. And oh dear. Okay, so I'm running very behind. So so I will just complete this case, and then case 2 is even much more complicated. Let's see this case in full and see what happens. Okay, so we got this here. Otherwise we have a contradiction, and let's see this here. So firstly, right, that's this red thing here is at least 2/3 n, and A prime is at most k minus 1. So the k minus 1, k minus 1. So that is, in fact, I put max n over 3, 5 over 2, k minus 1. Right, so we have this part, and let's see that this thing is k connected. So firstly, I will claim that this is a clique. So we are talking about this here. So obviously we have a clique in here. So this is a clique. And also everything here dominates here. So we just have to check two vertices over here. So let's check that. So if we have two independent vertices over here, then I can just, so A intersect L star, so X, so if you can see them, and they're independent, then I can just pick a Z anywhere in A prime. So it might be here, for example, and then they have to be independent from Z. Again, contradiction from that earlier observation. And finally, I've got to add these on. So once again, so I claim that everything here dominates this part here. So obviously that's true. And then if we are missing an edge between something here and something here, I can take a y in. So we have this earlier fact here. A prime intersect A1, 2 is not empty. So I can take a y in that set. So it would be like over here. So if that's Z, this is y. And then once again, independent triangle. Contradiction. Okay, so that's that subcase. Let me try and complete this one, and then I really don't have time now. So now this thing empty. So I claim that this is empty. So I have to show that with B2 here it's empty. So yes, so let's so I'm going to prove this first. So if otherwise we can pick so we assumed earlier this was non-empty, so we can pick this. We can pick this by assumption, and we can pick this as that's non-empty from back here. So and then they're independent. Another contradiction. So at least two of them are in A1. We can see that. So X is in L star, so it's in, and Y is in A1 too, so it's also in. Yes, X and Y are in A1. So that again gives us a contradiction. So therefore, we have this here because, yes, because A, so now this is true, so A does not meet B intersect L star, and neither does A prime, because A prime is, so because L star is up here, and A prime is down here, so it doesn't meet L star. So we have this here, it must be inside T. And this, yes, we use this fact here with two suitable further states to get this here. So yes, you can believe this, and then we do a calculation here. So what's happening here? So N is a subset of T. B intersect L star is a subset of T. And A12 union S2 star consists of only two parts. A part intersecting A prime and a part intersecting T. So it doesn't meet A here. And so I can split this up into an A prime part and a T part, which can be absorbed with these two terms and absorbed into this T here. And using this here, I get the K minus 1, so I have this upper bound. And then this, okay, so I might have to draw, let's say, one more picture. So and okay, so let's see what's happening. Right, so I'm going to find what this set and this set are. So obviously S2 is this one, and T prime unit, yes, T prime is this set. So without these two circles, and then B intersect L is that one. So that blue thing is that there. So right, and also, let's find what this is here. And this red thing here is this this whole thing here, which is at most 2 times k minus 1. Right, and notice that, in fact, this is actually contained, not equals. So what can we say? So therefore we have well, okay, with some calculations we get this here. So anyway, so okay, that's a contradiction to this fact here, right? This is obviously an S, and then this means that it's at most 2 times k minus 1, and it's too big here. Right, so that completes case 1. And case 2, well, there's a lot more facts to prove. I may need another hour to do it, I think. So, okay, so case 2 is this. So we assume now B2 does not meet here. So this is only B1 here, and B2 has to be inside here. And then we find out all of these things, and then put together an argument. I might need another hour, sorry. But okay. Open problems. Okay, I'll try to say it in about a minute. So the first one is, so we saw that we had very basically we have this thing here, and we know what's going on here and here. So this first problem is just asking at which point onwards are we able to get the k-connected subgraph on at least n over alpha? So where is this function f? Where is this optimal function f of alpha k? Right? So we know that it has to be more than, say, about 9/4 k, alpha k, roughly. And then for small n, so if we're, let's say, less than 9/4 times alpha k minus 1, then we know that we cannot get the n over alpha, but nonetheless, how large can we get instead for k-connected subgraph? So there are some other nice questions you can ask, but here are just like 2 problems here.
So you must know some kind of lower bound on this problem 6, no?
What, low bound on what?
How large you can, you know something, no?
I don't know anything except that it cannot be more than n over alpha. So I'm not sure what the answer is, because
You don't know n over 10 alpha or something?
Yeah, for example, yeah, something smaller than, let's say, n over constant alpha, for example. So that would be an interesting question to consider. Okay, so come send me the, thank you.